right. So in the last lesson, we said that ideal gases have a few qualities that real gases don't. And those were that ideal gases, they have their particles are in random motion with no forces of attraction. The average kinetic energy tells us about the temperature because it's directly related to that. Collisions are elastic, which means that overall kinetic energy remains the same. And these collisions produce pressure when they collide with the uh, with each other and with the container. Then they create pressure, and the size of these particles, the volume that these particles have, is much smaller than the volume of gas. Like it's not even comparable. And so that was how we figured out how the volume relates to the size of particles, that the distances between particles are huge and the size of these particles is really small. Similarly, temperature depends on average kinetic energy, and pressure depends on the collision and the strength of these collisions between these particles. But let's look at this graph. This is a graph of how uh, pressure and volume would change for any ideal gas. But so that's a straight line. All right, this green line in the middle, that shows how it should change, because P times V is a constant. We know that because Boyle's law says P is inversely related to volume. So if you multiply them, you get a constant, no matter what the volume or what the pressure. But in real terms, when we look at that, it's not really a straight line. In fact, for none of the gases that we know, it is a straight line. Sure, the gases do follow that for a small amount of time, maybe, but then they deviate. And this is called real gases, deviation from their ideal gas behavior. Okay, so deviation from ideal gas behavior. Now, we want to know why these gases do it. So let's again revisit the postulates that we had. Number one postulate was that particles are in constantly randomly moving, and the forces of attraction are really small. They don't exist, but in reality, they do exist. Similarly, we said that collisions are elastic, which means that they don't lose any energy when they collide. But in reality, that is not the case. When particles collide, especially when they collide with the container, they do transfer some of their kinetic energy to the container. That is why when we, for example, touch a cylinder that has cold gas, that cylinder will feel very cold because the cylinder walls will transfer the heat from our hand to the gas. Similarly, if we touch a warm cylinder, that is because the particles inside are radiating or emitting heat that is coming out. So there is a collisions are not being perfectly elastic, not elastic. So that's the case over there. Similarly, there are cases where the volume of particles, so volume of particles, the total volume of these particles is comparable to container. Not in large containers, of course, because containers can be huge compared to the size of these molecules. But if you have really small volume, like if I were to compress a gas and I had a syringe that was really small and it had gases, or another container that was tiny in which the particles, I compress the gas to a large extent. So then it is possible that the total volume of these particles is a significant portion of that container, maybe 10%, maybe 12%, maybe 25%, depends on the size of the container. So it is possible that at very small volume, these particles do constitute a big portion of the container. So then they will not be entirely insignificant, or the volume will be important. We will have to consider that. So none of the gases give the ideal gas behavior, as we know. Now, why is that? These three reasons. So force of attraction, it's not technically zero. Sure, it is weak, but what if these particles had high temperature? Then they're constantly coming close together, bouncing off each other, and they're going away. That's fine because the forces are weak, the temperature, the kinetic energy is high, they're bouncing off. But imagine if I had a gas and I cooled it down, then these particles don't have enough energy to go away, especially if temporary dipoles form when one particle approaches the other. So now there are forces that are not letting it go away. And when it tries to go away, the forces are going to slow it down, because one particle is going to pull on the other particle, because there is temporary dipole. Ideal gases don't have that, but real gases do, which means that if you had a gas in which there will be strong forces of attraction, then it will deviate more from the ideal gas behavior, because the collisions are going to be sticky. The particles, when they collide with each other, are going to want to stay together because forces pull them together. That's one. Similarly, uh, because the forces are not important, they are important now, and the collisions are no longer elastic, the average kinetic energy is going to change a little bit based on how long the particles have been colliding with each other. So they are going to lose some energy. So they're not elastic, they're going to lose or gain heat energy. And then the volume of particles, especially when the container is really small, is a big portion, which means you can't really ignore them, which means, again, it's not ideal gas. So for our intents and purpose, we just need to consider one thing. The stronger the forces of attraction, the closer they pull the particles. The significant effect, the more significant their effect on these collisions are. So अगर एक particle दूसरे के पास आता है, वो उसको close pull करता है, वो उसको sticky करता है उन collisions को, doesn't let them go away, which means they lose energy. In that, obviously, they're losing energy to fight these forces. They're slowing down in the process, and the force of attraction is significant. Now let's look at this. There is a gas, hydrogen and helium, and both of these have temporary dipoles in them, right? And because of those temporary dipoles, the force of attraction is really weak, especially in hydrogen and helium, which are really small.
Sir, can you hear me?
I can.
Sir, can you repeat why, like, the strong force of attraction, and then the closer they pull each other, and then like the third point?
Yeah, so let's consider these two particles. This is approaching this one. This is randomly moving in place. But as soon as this approaches this, right now they're neutral, but as soon they approach each other, they're going to get temporary dipoles, because the electrons of this one are going to be repelled, creating a slight positive charge on this side, creating a negative attraction to the electron towards this side, creating another dipole here. So there's a slightly positive charge here, slightly negative, slightly positive, slightly negative. And now if I were to move this atom away, these forces are going to pull them closer. So जितनी जल्दी वो वापस आया था, वो bounce करके उतनी जल्दी दूर नहीं जा सकता, because it's being attracted by that dipole now. And so if it has enough energy to go away, if it has enough inertia to go away, still it's going to lose some kinetic energy fighting these forces of attraction. So the collisions are not elastic anymore because the particle has lost some energy. So when you have an ideal gas, वो 20 डिग्री सेल्सियस पे है, मैं उसको रख देता हूँ, वो हमेशा 20 पे ही रहेगी, because the collisions are elastic. It's never going to go up to room temperature. And if I have steam at 105 degrees Celsius, it's going to just collide with each other, and it's never going to come down to 25 degrees Celsius. But real gases don't do that. Real gases actually lose that energy, the extra energy or the extra energy that they have at 105, and they are going to go down to 25 degrees Celsius, the room temperature. Similarly, real gases will cool, which are already cool, they will warm up and reach the room temperature if you let them. Ideal gases aren't supposed to do that. And again, the reason is that their collisions are not entirely elastic anymore. They are gaining or losing kinetic energy. Similarly, their forces of attraction are significant, and they become more and more significant the closer, the stronger the forces they have. So if you look at this, can you think of a reason why oxygen, which is also having temporary dipoles, and helium and hydrogen, which also have temporary dipoles, why is oxygen's deviation more from ideal gas behavior?
Sir, because it's a larger atom, so
It's not an atom, it's a larger molecule.
Sorry, it's a larger molecule, so it'll have stronger dipole moments.
You're missing a link over there. Why does being a larger molecule
Because it
translate?
has more protons and electrons.
Not protons, just electrons. That's the significant. So it's only the electrons, because electrons are shifted from one side to another side. Protons तो वही center में है ना. So yeah, you're right. Because it has more electrons, the dipoles that are created when they come close to each other or when they collide, they are much more stronger. And the force of attraction is stronger, which is why the deviation is more. Similarly, why is it that HCl, because HCl has 16 electrons, 18 electrons, and O2 has what 16 electrons. इतनी ज्यादा difference क्यों है? इतना ज्यादा होना नहीं चाहिए. मतलब if I were to draw that for argon जिसमें 18 electrons होते हैं, तो वो इतना ज्यादा behave ना करती, वो शायद ऐसे चाहती. Why is it that HCl is deviating a lot compared to oxygen?
Yeah, because HCl has permanent dipole.
Exactly, very good. So HCl has permanent dipole, and those permanent dipoles have even stronger forces of attraction. So the collisions are more sticky in HCl compared to O2. And in ammonia, you can clearly see that ammonia, just along these lines, it has hydrogen bonding. So not only does it have permanent dipoles, those permanent dipoles are a special kind, the hydrogen bond, which is much, much stronger. So its effect is even more pronounced. If I had steam over here, how would the graph change for steam?
Sir, would it be the same as ammonia? Or like deviate a bit more than ammonia?
It will deviate more than ammonia because its hydrogen bonding is much stronger. So that is how it would be. So here's the thing. The hypothetical ideal gas that we have, the perfect gas, they follow the PV is equal to nRT, the ideal gas law, for all conditions of temperature and pressure. And the primary two factors that are important there is, number one, there is no force of attraction between these molecules. And number two, the volume of molecules themselves, or the volume of the atoms themselves in the ideal gas, is insignificant. But that's not the case in real gases. There is no zero attraction, and we can't really ignore the volume. So when do you think these differences between these gases are more noticeable or more pronounced? Obviously, when the molecules are really close to each other. Why? I'm talking about real gases. If they're close to each other, why are they deviating more from ideal gas behavior?
Because the forces of attraction are more between them.
Exactly. When
So
they're far, the forces are weak. When they're close, the forces are stronger. So the deviation is stronger. Secondly, because they're close together, the volume of molecules is not negligible compared to the volume of the container. So the van der Waals forces are stronger, and they pull them close together and away from the walls of these containers. So the volume of the gas is much smaller than you would expect an ideal gas to be. So because an ideal gas is pulling the particles, the particles are not that close together in ideal gas, but when these molecules are close together, their volume is less compared to what an ideal gas would be, which is why you have this portion, this whole portion.
Sir, I don't understand the second point.
So here's the thing. When you have high pressure, this high pressure, when you go towards the right side, the volume is much smaller compared to what the volume of ideal gas should be. हमने ideal gas की एक volume सोची हुई है कि इतनी होनी चाहिए, लेकिन जब हम real gas की volume उसकी देखते हैं ना, तो वो high pressure पे उतनी नहीं रहती, वो उससे कम होती. Let's suppose ideal gas की volume होनी चाहिए थी 10 centimeter cube. Real gas की volume हम measure करते हैं, पता लगता है वो 7 centimeter cube है. वो ऐसा क्यों है? Because at high pressure, the particles are much close together, the forces are much more stronger, they pull them towards each other more than an ideal gas would, क्योंकि वहां पे तो forces है ही नहीं. And that is why you're seeing these minimums. ये जो नीचे को आ रही है ना,
So these volumes, so the volume becomes less?
yes. If
Wouldn't that
oxygen
make
was an
it more
ideal gas, if oxygen was an ideal gas and we fix the pressure over here, then we would expect कि oxygen का यहाँ पर pressure times volume आना चाहिए था. लेकिन actually में वो ये होता है, उससे भी कम value आती है volume की. क्यों? Because the forces are stronger. Similarly, if we fix the volume of pressure over here, if we fix the pressure over here, then we would expect an ideal gas to have this value for pressure times volume. But in HCl, that's not the case. In HCl, we get this. In ammonia, we get this. Much, much smaller volume than we would expect an ideal gas to be. मतलब ideal gas की ये होनी चाहिए और HCl की ये है और ammonia की ये है. क्यों है ऐसा? Because the forces of attraction at high pressure are pulling them close together.
Then why does it increase after that?
Why does it increase? Because then there comes a point जहाँ पे obviously you can't just keep pushing them close together. उनका temperature भी change करता है and the particles do bounce away from each other क्योंकि you can't just keep compressing them. वो एक दूसरे को repel भी तो करते हैं electron clouds, तो वो दूर चल जाते हैं फिर उसके बाद. Kind of like an explosion. If you keep pushing them closer and closer and closer and closer, they will eventually repel much more strongly than you're pushing them close together. आप उनको particles को पास लेके आ रहे हो और particle एक दूसरे को repel कर रहे हैं. There will come a time when the repulsion is much more stronger, which is why they start to rise, even at high pressure. So there is one case where they become liquids. You push them close together, they change their state. वो liquid बन जाता है. And there is another case where you let them stay as a gas based on temperature and all that. कि वो liquid ना बने. But if you push them very close to each other, they are going to go like explode or something. Get it? Because the repulsion of these electron clouds is going to push them further away, even if you keep adding more pressure. So एक minimum जो आ रहा है ना, वो इसीलिए आ रहा है because the forces of attraction over there are much, much stronger and their effects are much more pronounced. But helium or hydrogen में minimum आ ही नहीं रहा. Because they don't compress more than you would expect them.
So I don't understand this.
What part? What's the question? Can't be confusion.
Why helium and hydrogen don't have like a peak?
They don't have a peak. They have a minimum point.
Yeah, like sorry, why don't they have a minimum point?
Because they don't have very strong forces of attraction. Their forces are negligible. Number one, their clouds don't have many electrons. बहुत ही कम है. So the dipoles that they generate, even if you pull them close together, are negligible. इसकी वजह से they don't compress more than you would expect them to. But the only reason oxygen का नीचे आ रहा है, इसका नीचे आ रहा है, इसका और नीचे आ रहा है, is because when you push them close together, वो उनके dipoles उनको और close pull करते हैं. मतलब आप बाहर से externally उनको push कर रहे हैं, but the dipoles themselves pull them much more closely together. So in an ideal gas, you would expect it to have this volume and multiply to give us this PV. But in a real gas, in HCl, you get this, a smaller volume than you would expect. Similarly, in ammonia, you get a smaller value, a much smaller volume than you would expect in a real gas or in an ideal gas. So ideal gas में आप expect करते हो कि ये आएगी जब आप pressure इतना fix कर दोगे. But real gas में आप ammonia में देखते हो कि वो तो इतनी से आ रही है, इतनी नहीं आ रही. And the difference is because ammonia has much more stronger dipoles which pull the molecules much closer together. मतलब आप कह रहे हो कि molecules जो हैं वो ammonia में यहाँ इतने दूर रहेंगे, लेकिन because the forces are stronger वो इतने दूर नहीं रहते, वो और close आ जाते हैं. And then there comes a time when you push them close together and you expect कि अच्छा इतना सा होगा उनका distance. But in ammonia ऐसा नहीं होता because the cloud repels so much strongly कि even at high temperature वो दूर चले जाता है. तो उसकी वजह से उसकी वॉल्यूम आइडियल गैस पे आप एक्सपेक्ट करते हो कि इतनी होगी, लेकिन रियल गैस में वो इतनी हो जाती है, which is this portion, which is this portion, which is this portion. This is where the forces of attraction are not working towards compressing it as much as the repulsion from these electrons towards each other. So you have two clouds, you're pushing them towards each other, they have dipoles, वो dipoles एक दूसरे की तरफ उनको further pull करते हैं, so they're working in sync. You're also pushing them, they're also pulling closer to each other. But then they reach a certain point after which the repulsion of these electron clouds is more, and आप उनको अंदर को compress कर रहे हो, but उनकी repulsion बहुत ज्यादा है. it's working against your efforts. तो अब आप कहते हो कि अच्छा वॉल्यूम अब ये होनी चाहिए, लेकिन गैस कहती है मेरी तो वॉल्यूम अब ये होगी. आप कहते हो यू वुड एक्सपेक्ट कि मैंने इतना प्रेशर लगा दिया है तो अमोनिया की ये वॉल्यूम के साथ मल्टीप्लाई होकर आना चाहिए, बट अमोनिया का एक्चुअली में ये आता है. क्यों? क्योंकि व्हेन यू apply that much pressure on a gas that has a lot of electrons, 34 electrons in the cloud, when they approach each other, the repulsion is much more stronger. तो एक दूसरे को push away कर देते हैं. So you have two things, the repulsion between the clouds and you have the attraction between the dipoles.
Yes, sir.
Okay, great. अगर फिर भी confusion है तो पूछ लो. Okay, so I have four gases: carbon dioxide, helium, hydrogen, nitrogen. Carbon dioxide, helium, hydrogen, nitrogen. Which of them is going to act the least like an ideal gas?
Sir, carbon dioxide.
Why?
It has the strongest intermolecular, like it has more electrons and has molecular forces.
Yep. The dipole that is going to get is going to be much more stronger than the other gases. That is the case. All right, so that was the main idea of what we needed to know in ideal gases, and obviously how the real gases deviate from there. So the questions that are usually asked are, number one, which gas deviates the most? वो MCQs में पूछ लेता है, या वो आपको reason पूछ लेता है in paper 2 that why is this that ammonia deviates more than hydrogen, or water deviates more than ammonia. So it's all about the forces of attraction and the number of electrons in the cloud. Second is about understanding, identifying a graph. So for example, they might give you a graph and they might expect, okay, I have volume here and I have pressure times volume here. So for a real gas, for an ideal gas, what should the graph be? So for an ideal gas, you know that pressure times volume is a constant according to Boyle's law. So you'll say that it's supposed to be a straight line according to ideal gas law. And then they're like, all right, what is the behavior of a real gas? और आपको वो ग्राफ दे देंगे. तो ग्राफ में आपने देखना होगा कि अच्छा अगर मेरे पास रियल गैस होती तो उसकी वॉल्यूम, अगर अच्छा वॉल्यूम का ग्राफ नहीं आएगा, उस पर प्रेशर का ग्राफ आएगा यहाँ पे. मतलब अगर प्रेशर वॉल्यूम में से कोई भी हो ना तो आइडियल गैस का तो ये ग्राफ होता है, बट आपको जो रियल गैसेस का ग्राफ आएगा ना वो प्रेशर के साथ होगा. तो देन यू विल बी लाइक ओके हाइड्रोजन हीलियम डू नॉट डेविएट बट अमोनिया डज और ऑक्सीजन डज और steam does and all that. Okay, so this is a deviation that you're going to show. Similarly, वो आपसे पूछ लेता है कि if volume is kept constant, then how is the graph of on this side I have pressure divided by temperature, on this side I have temperature, and I'm keeping volume as constant. So what do you expect this to be? So this is clearly the idea of a Charles law, Gay-Lussac's law, that pressure is directly related to temperature. So you will draw a straight line. Similarly, they might expect Avogadro's law, जो कि बहुत rarely question आता है, कि if you have more number of moles and you have volume divided by that number of moles.
How do we know the one above is a straight line?
Because if you look at any law, what do you get? So आपके पास एक law है ये, P is directly proportional to temperature. And if I were to convert it to an equation, I get P is equal to KT, right? Which means P over T is equal to K, a constant.
Yes, sir.
Okay. Another way to do this, कि आप चार different laws की बजाय एक ही law से अगर इसको करना चाहो, so for that you have PV equals nRT. Okay. Now, if they say, okay, what is the graph of PV compared to P? Then what you should do is that take the ideal gas law and ignore any factor that is constant. Malab, in this graph, they have told you that temperature is constant and number of moles is obviously constant, even if they mention it or not. Unless they say the number of moles is changing, only then you keep that. So, agar main isko PV equal to nRT को without temperature, without number of moles लिखूं, तो मुझे मिलेगा PV is equal to R, which means R is a constant, so PV is equal to going to be this, which is 13.6, 13.1, 8.31, sorry. तो उसकी value fixed 8.31 पे होगी. वो आपसे कहता है कि नहीं नहीं, your graph is supposed to be between temperature and pressure divided by temperature. then you're like, all right, wait a minute, I need to ignore volume now. So volume को ignore करके इस ग्राफ को इसको लिखो, तो आपके पास बनता था P over T is equal to R. मतलब मैंने इसमें वॉल्यूम और नंबर मोल्स को इग्नोर किया है. So I'm getting P over T is equal to R, which is a constant. So now I'm going to get a 8.31. वो आपसे कहता है कि what is the, वो Avogadro's law को चेक कर रहा है. वो कह रहा है कि अच्छा, what is the graph of V over N compared to volume? So like, all right, I have PV is equal to nRT, but I'm going to ignore everything that's not in the equation. So I ignore pressure, I ignore temperature. So that gives me V over N equals to R, which is 8.31. So it's going to be a straight line. Get it? So in MCQs, they ask you for these graphs. That is ideal gases. Any questions in that? Obviously, paper 2 में एक और सवाल आता है, paper 1 में भी आता है, that use the ideal gas law at this temperature to find out the volume. और अगर उसने ज़्यादा उसको complicated करना हो तो वो क्या कहते हैं, that same gas but at 25 degrees Celsius and at 100 degrees Celsius, compare the change in volume. So आप आइडियल गैस लॉ निकालोगे, दोनों टेम्परेचर पे वॉल्यूम देखोगे और फिर उसको माइनस कर दोगे. So that is another paper 2 or paper 1 question that they give you. So that is the whole story of gases. In liquids, there is one concept that we need to know. In fact, two. एक तो हमने O levels में जितना कुछ पढ़ा है, I'm not repeating it because I'm assuming कि kinetic theory in O levels it's beaten up so much कि हर बच्चे को आती होती है. If you are one of the students जिसको नहीं आती तो मुझे पूछ लेना. So in liquids, we know that liquid is basically a temporary stage or an intermediate stage between a solid and a gas, because solids are extremely opposite to what gases are. So solid में particles पास पास होते हैं, gas में दूर दूर होते हैं, और liquid बीच में कुछ है. And solid में particles have very low kinetic energy. Gas में बहुत ज़्यादा है, और liquid बीच में कुछ है. So liquid is always an intermediate thing. So we just need to understand solids and gases and then take a mix and match of that thing to understand what a liquid is. So liquids can be complex in that regard कि वो कौन सी properties gas की लेगा और कौन सी properties solid की लेगा. And again, that depends on the forces of attraction between a certain thing. So if there is a solid that is melting with very strong forces of attraction, so we would expect its melting point to be high, its boiling point to be high, that the liquid is also going to have strong forces of attraction. We are going to expect the liquid to have higher density. And that is why molten metals have high density, because the molten solid has high density. The solid has higher density. Molten solid kya hota hai? Similarly, if there is a solid that has weak forces of attraction, we would expect the liquid to be quite volatile, because the liquid will also have weak forces of attraction. So basically, energy that you provide to a solid melts it and breaks the forces to some extent and creates distances between the particles in a solid, converting them to a liquid state. But liquid is just an intermediate before it goes on to become the gas. And the behavior, the physical properties of that thing don't really change if it becomes from solid to a liquid. तो जो उसकी solid की properties हैं वो थोड़ी सी weak हो जाती हैं, but liquid में वही transfer जरूर होती है. There is one concept that liquid has that isn't really that much in solid, and that is evaporation. That liquid particles evaporate. Solid particles don't evaporate. They do diffuse much, much slowly, like maybe a couple of inches in 100 years or something. But in liquids, they do evaporate, and some liquids evaporate at a very high rate. In fact, that when we are doing the reaction for those things in lab, we make sure that we use a reflux condenser, which is nothing but a vertical condenser. ऐसे place किया होता है उसको, and इधर से liquid आता है, इधर से liquid जाता है, and we just make sure, sorry, इधर से, yeah, and we just make sure कि for example ये round bottom flask है, तो इसमें liquid को heat कर रहे हैं, तो ये evaporate तो हो लेकिन वापस आ जाए, because we want it to stay in the flask, the round bottom flask, but we don't want it to go away. We don't want it to evaporate, but we also don't want to put a stopper, because there'll be a buildup of pressure of gas and it might explode. And this is called a reflux condenser. And again, we use it when we have volatile liquids reacting. So volatility is a factor of how soon or how fast something evaporates. And again, evaporation is that there are particles in there that have high temperature and they just high energy. not high temperature, they have high kinetic energy and they just evaporate, और वो दूर दूर चले जाते हैं और वो गैस में कन्वर्ट हो जाता है क्योंकि वो पार्टिकल्स इतने दूर हो जाते हैं कि now it is effectively a gas. And then as you give them more kinetic energy, there are more particles with high kinetic energy, so they evaporate. So if I have a liquid in here and there's a particle in here, this particle has high kinetic energy, so वो क्या करेगा, वो bounce होता जाएगा और वो इधर उधर मूव करता जाएगा. But if there's a particle here that has high kinetic energy, तो वो क्या करेगा, या तो वो नीचे जाएगा या वो ऊपर चले जाएगा. And if it goes away, we say that it has evaporated. And evaporation is that now the particle is so far away from other particles of the liquid that it has effectively become a gas. But of course, to do that, there are two things that it must do. Number one, it must fight off the forces of attraction जो liquid के अंदर में थी. And it can do that because it has high kinetic energy compared to the rest of the molecules. But also it must fight off the forces of the pressure from the atmosphere, and not just atmosphere. Sometimes ये भी होता है कि आपके पास बहुत से liquid के particles already evaporate कर चुके हैं और जो evaporate कर रहे हैं वो भी तो bounce off कर रहे हैं ना, तो वैसे randomly move कर रहे हैं, and some of them are coming and hitting the liquid surface, and this is called an interface. Interface is wherever you have two different states interfacing with each other. So होता क्या है कि there are some particles that are going up, down, all of the directions, but फर्क ये है कि liquid में वो close हैं, gaseous state में दूर दूर हैं, और ये जो vapors हैं, they are hitting the surface. So the pressure with which these vapors hit the surface, we call that vapor pressure. And what happens is that at all times, some molecules in the liquid are evaporating, वो ऊपर को जा रहे हैं, some of them are going up, and at all times, some of the gaseous particles are also coming down and mixing with the liquid that you have and coming back and becoming a part of the liquid state. So it's not just कि evaporation ऊपर को ही होती है, particles जो already vapor हैं वो वापस condense भी तो होते हैं, वो वापस liquid में आते तो हैं. So they create an equilibrium that there is the particles that are liquid and particles that are in vapor, and they're constantly coming back and forth, like one particle ऊपर चले गया, दो नीचे आ गए, and somehow when you get an equal rate of this movement, that the liquid particle going into the gaseous state and the gaseous particle going back to the liquid state, when the rate is equal, that is an equilibrium, right? And at that equilibrium, the vapor pressure is the pressure exerted by the vapor on the liquid. So जितने pressure से वो ऊपर वाला liquid वापस liquid की surface में आ रहा है ना, जो ऊपर जो vapors हैं, at the equilibrium, it's important to have the equilibrium, then that is called vapor pressure. And interestingly, the moment
Can you repeat the definition for vapor pressure again?
vapor pressure is pressure exerted by vapor particles on liquid surface जब आपके पास ये equilibrium होगा, when there's an equal rate of particles becoming a liquid compared to the particles evaporating. So equal rate of movement of particles in the liquid and the vapor. When that happens, when that equilibrium stage is approached, the pressure exerted by vapor particles on the surface is called vapor pressure. Now, interestingly, when this vapor pressure becomes equal to the atmospheric pressure, कि मतलब आपके पास उस liquid के उसके इतने particles evaporate कर गए हैं कि वो जब वापस आ रहे हैं और जो ऊपर को जा रहे हैं, एक तो वो equilibrium में आ गए हैं, and secondly, the pressure that they exert, for example, water की example ले लेते हैं. Water vapor that you have, the pressure that those vapors exert on the water surface is exactly the same as the pressure from air. कि मतलब air भी उतना ही pressure apply कर रही है जितना वो liquid जो evaporate हुआ था वो कर रहा है. सो वाटर के अपने मॉलिक्यूल्स का प्रेशर और एयर का प्रेशर दोनों बराबर हो जाते हैं. एंड व्हेन दैट स्टेज कम्स, लिक्विड बॉइल्स, तो वाटर बॉइल कर जाएगा. सो व्हाट इज बॉइलिंग पॉइंट? Boiling point is temperature at which vapor pressure equals atmospheric pressure. Now here's a very interesting part. If I want to boil water at room temperature, I don't want to heat it, I just want to boil it. तो मुझे क्या करना चाहिए? I should reduce the atmospheric pressure. Because हम बचपन से सुनते आए हैं since 6th grade science book that when you're cooking in mountainous areas, you add more salt to your whatever thing you have, or you use a pressure cooker. Why do you do that? Because you want to increase the atmospheric pressure on that thing. But because the atmospheric pressure in general is low, water boils first. Water 96 डिग्री सेल्सियस पे बॉईल कर जाएगा 100 की बजाय, आपका खाना कच्चा रह जाएगा. So if you don't want to do that, you increase the pressure. So water doesn't evaporate even if you have reached the technical boiling point of that thing. क्योंकि प्रेशर कुकर में पानी बॉईल करने नहीं देते हम. क्यों? क्योंकि उसके ऊपर वेपर प्रेशर जो है वो 100 पे बहुत वेपर प्रेशर होता है, लेकिन एटमॉस्फेरिक प्रेशर और ज्यादा हो जाता है, जिसकी वजह से वो इवेपोरेट नहीं कर पाता. क्योंकि जब तक वो एटमॉस्फेरिक प्रेशर को मैच नहीं करेगा ना, liquid will always differentiate from the gas and the atmosphere. It can't be a part of the atmosphere, the whole liquid. Boil नहीं कर सकता वो तब तक. So अगर आपने boil करना है, just make sure that you reduce the atmospheric pressure to the vapor pressure. तुम उनको match करवा दो, या vapor pressure को increase करते हो और वो atmospheric pressure को match करता है, which is how we normally boil stuff. हमने पानी boil करना है, we will heat it, we'll give it so much energy that the particles bounce back and forth इतनी तेजी से that now they are having the same pressure as the atmosphere, जो कि 100,000 pascals होता है. And the other option is you put them in a container and that container has low pressure. And when it has low pressure, the liquid, whatever vapor pressure it has, उसको जब match करवा देगा atmospheric pressure, automatically boil कर जाएगा. उसकी वजह क्या है? उसकी वजह ये है कि जब लिक्विड इवेपोरेट हो रहा है ना, सो उसमें कुछ पार्टिकल जिसमें इतनी एनर्जी है कि वो एटमॉस्फेरिक प्रेशर को मैच करते हैं, बीट करते हैं और वो गैस का पार्ट बन जाते हैं. लेकिन सब पार्टिकल्स में उतनी एनर्जी नहीं होती. बट व्हेन they have the same energy as the atmospheric particles around them, और सबके सब में उतनी हो जाती है, क्योंकि वेपर प्रेशर क्या है? इट इज द प्रेशर एक्सर्टेड बाय वेपर, जो ऑलरेडी चीजें इवेपोरेट हो गई हैं और वो सरफेस के ऊपर पुश कर रही हैं और सरफेस के पार्टिकल्स को ऊपर नहीं आने दे रही. तो अगर एक वक्त ऐसा आए कि सरफेस के पार्टिकल्स को जो प्रेशर हवा लगा रही है वो उतना ही हो जितना वाटर वेपर कर रहे हैं, so there's technically no difference as far as the resistance these liquid particles experience. So सारे के सारे liquid particles will jump up and become a part of the gas, and that is why it boils. So another important concept that is tested here is, number one, what is boiling point? What is vapor pressure, the definition? What is the relation between boiling point and vapor pressure? Similarly, if you decrease the atmospheric pressure, what effect does it have on the boiling point? If you increase the atmospheric pressure, what effect does it have on the boiling point? Similarly, liquids that have stronger forces of attraction, what is the boiling point of those liquids? Uska bada simple सा है that their vapor pressure is low compared to other liquids जिनका vapor pressure ज़्यादा होता है. So why does alcohol boil before water? It's simple. Water has stronger forces of attraction. तो at 78 डिग्री सेल्सियस वाटर का वेपर प्रेशर उतना नहीं होता कि लिक्विड सारा इवेपोरेट कर जाए या लिक्विड सारा बॉईल कर जाए. बट अल्कोहल का होता है, बिकॉज अल्कोहल में उतनी स्ट्रॉन्ग फोर्स ऑफ अट्रैक्शन नहीं होती, तो उसकी वजह से वो उतना प्रेशर अप्लाई कर रहा होता है जितना एटमॉस्फेरिक प्रेशर अप्लाई कर रहा होता है, तो वो बॉईल कर जाता है. सो व्हाई इज इट दैट alcohol boils at 78 and water doesn't? It's because at 78 alcohol particles, because उनके अंदर force of attraction बहुत weak है compared to water, वो bounce back and forth ज्यादा कर रहे होते हैं. Water molecules उतनी जल्दी bounce back नहीं कर रहे होते, वो एक दूसरे को pull कर रहे होते हैं. तो वो इतना फ्री नहीं है. जब इतना फ्री नहीं है तो जाके जोर से लगता नहीं है, उतनी जोर से लगेगा नहीं तो प्रेशर उतना नहीं बिल्ड कर पाएगा. एंड दैट इज व्हाई at 78 water particles are basically pulling each other back. वो एक दूसरे को अट्रैक्ट कर रहे होते हैं, तो उतनी फ्रीली मूव नहीं कर रहे होते, और उस वजह से उनका प्रेशर एटमॉस्फेयर प्रेशर के बराबर नहीं हो पाता. क्योंकि वो इमेजिन रनिंग इन अ रेस व्हेन समबडी इज पुलिंग यू बैक, आप वो उतनी तरह से उतनी तेजी से निकल नहीं पाओगे ना. बट अल्कोहल पार्टिकल्स, उनकी फोर्स ऑफ अट्रैक्शन वीक होती है, तो एट 78 डिग्री सेल्सियस वो इतनी तेजी से बाउंस ऑफ कर रहे होते हैं कि वो एटमॉस्फेयर प्रेशर को मैच कर जाते हैं. वाटर नहीं कर पाता, तो अल्कोहल बॉयल हो जाता है. एंड वी यूज दैट, द डिफरेंस दैट वी हैव when we are doing fractional distillation. All right, so that was the key idea of liquid becoming a gas, and obviously the ideal gas behavior and real gas deviating from that. Everything else in this temperature, it's just the way it is usually taught in O levels.